In 7.4, we're going to start working with exponential functions by writing and graphing exponential growth functions. Exponential functions have two different types. They have growth functions and decay functions. So we're going to be working right now on writing and graphing exponential growth functions. And our vocabulary is what is an exponential function, what specifically is an exponential growth function, and what is compound interest. And when you think about exponential growth functions, they're normally in their simplest forms, y is equal to a times b to the x power. All right, and the reason they're called an exponential function is you'll notice that our variable x is now an exponent. And if the value of b is greater than 1, it's a growth function. And if the value of b is between 0 and 1, it's a decay function, okay, which we'll deal with in another section. And the concept of compound interest is interest that is earned on other interest. So as you calculate interest, if you roll the interest back into the principal and then earn interest on it again, that's what creates compound interest. So if we want to look at an exponential function, as I said before, it's y is equal to a times b to the x. And what we're going to be looking for is what's the value of b. Okay, so they're nonlinear functions. In fact, when I'm talking about a growth function, it comes in basically horizontal and it finishes basically vertical. Okay, so it has a curve, and this is what a growth function would look like. If I wanted to write the rule for this function, I would want to start looking at how could I figure out what was going on in this function. Okay, so I know that x is -2 when y was 5, so 5 would be equal to a times b to the -2 power. And I know that when x was 0, which is a very telling time, that's a very important one to know, y was 125. So 125 is equal to a times b to the 0 power. And I say it's a very telling time because I know b to the 0 power would be equal to 1. So if 125 is equal to a, then we can start figuring out what's b equal to, right? So if I go ahead and take the value of a and plug it back in here, 5 is equal to 125 times b to the -2 power. And if I go ahead and divide by 125, 5 over 125 is equal to b to the -2 power. And if I simplify this, this is going to be 1 over 25 is equal to b to the -2, which would also be equal to 1 over b squared. So then I know that b squared is equal to 25, so b is equal to 5. Okay, so when I write my equation, y is equal to a, which is 125, times b, which is 5, to the x power. Okay, and that's the rule right there. Okay, if we want to look at graphing an exponential growth function, what I'm very concerned with, remember it comes in horizontal and it goes vertical. What's most important to me is this area here where it changes from one to the other. Okay, and the easiest way to find those is to use some specific values of x. And this is a good rule of thumb a lot of the time. I want to know what happens when x is negative, what happens when it's 0, and what happens when it's 1. Okay, so if I go ahead and plug -1 in here, y was 1/7. When I plug in 0, 7 to the 0 power is 1, and 7 to the first power is 7. And if I go ahead and graph that, at -1, I'm at 1/7 way down here. At 0, I'm at 1, and then 1, 2, 3, 4, 5, 6, 7. I'm here, so you can see I come in horizontally here. I'm still basically horizontal, and all of a sudden, oops, I did a bad job with that. All of a sudden, it starts heading up to the sky. Okay, and that's how you graph it. But these values here, -1, 0, and 1, those are typically the values of x that I would choose to plug in to find out what my graph is doing, because it lets me know what happens when x is negative, what happens when it's 0, and what happens when it's positive. Okay, and this is a very easy way to evaluate any function, but for exponential growth functions, it normally gets you right to the best graph. Okay, if we wanted to compare different graphs of exponential functions, here we have y is equal to 3 to the x power, and I know that when I'm at -1, I'd be at 1/3. About here, 0, I'd be at 1, and with 1, I'd be at 3. So this is what this graph looks like. If I change colors for this graph and I use -2 times all those numbers, when I was at 1/3, if I multiply it by -2, I'd be at -2/3, so about here. When I was at 1, I'd be at -2, and when I was at 3, I'd be at -6. 1, 2, 3, 4, 5, 6, right there. So you see what happens is it inverts because it's negative, and then because it's 2, it also makes this curve, this turn, much faster. Okay, if we multiply it times 2/3, right, if we multiply it times 2/3, when I was at 1/3 times 2/3, that's 2/9. So I'm even closer down to the x-axis. When I was at 1, I'd only be at 2/3, so it's a little fatter. And when I was at 3, I'd only be at 2. So a leading coefficient that's less than 1 tends to flatten it out. When it's more than 1, it tends to stretch it out, right? And you're going to see that here with, we'll use a dotted line on this one, when it's 4. Right? So at -1, I'd have 1/3 times 4 is 4/3, so that's 1 and 1/3. It's all the way up here now. And when I'm with at 0, 3 to the 0 power is 1 times 4 is 4, so 1, 2, 3, 4, so it's way up there. And then -3 to the first power is 1 times 4 is 12, so that's way up here. So now we're coming in here and then shooting up. So it becomes even steeper than it was before. Okay, so you can see that the leading coefficient is going to amplify whatever's happening around the curve. The bigger it is, the steeper the line. The smaller it is, the flatter the line. If it's negative, it turns things upside down. Okay? That's what happens with that. When we talk about calculating exponential growth, we typically use a different model like this one. And this is an exponential growth model for annual interest. Okay, there's actually a more elaborate formula. Y is equal to A times 1 plus R over N to the nt power, which you'll work with later, where n is how frequently per year we calculate the compound interest. So we can work with this to be more whatever frequency we want. But for now, we're going to work with this simplified version that is for annual compound interest. So A is our initial amount, so whatever amount of money we start with. R in here is what's called the growth rate. right? And it has to be a positive number or it won't be growth. If it's a negative number, it'll become a decay rate. And t is the time period. And this item inside the parentheses, 1 plus r, is called the growth factor. Okay, so all these things have names. R is the growth rate, 1 plus r is the growth factor, t is time, and a is your initial starting amount. So if we look at working with that formula, remember the formula is y is equal to a times 1 plus r to the t power. Now if we have a problem like this, the owner of a car, a Hudson Hornet convertible, he sold the car at auction. He bought it in 1984 when its value was $11,000, and the value of the car increased at a rate of 6.9% per year. Write a function that models the value of the car over time. Okay, so when you look at it, 11,000 is our initial amount. So y is equal to 11,000. That goes in for A. And 6.9 is our growth rate. But 6.9% in this formula has to be written in as a decimal. 0.069 t. Okay, and if I wanted to simplify, this would be 11,000 times 1.069 t. Okay, if the auction took place in 2004, what's the approximate value of the car at the time of the auction? So how much time has passed? From 1984 to 2004 is 20 years. So I'm going to plug 20 in for my time. So I'll have 11,000 times 1.069 to the 20th power. So I'm going to have to do exponent first. I'm going to whip out a calculator here. So I have 1.069 to the 20th power equals this value, and then I'm going to multiply it times the initial amount, 11,000. So it's $41,777.92. Okay, I only round it to 2 decimal places because we're talking about money. So we only go to cents when we're talking about money. Let's take a look at another problem. Again, that was a compound interest problem. So was the previous problem. Compound interest is interest earned on both an initial investment and on previously earned interest. And we're going to use that same formula. So if I deposit $125 into a savings account, that's going to be my A value, my starting dollar amount. It earns 5% interest, so I'm going to have 1 plus 0.05 to the t power. Okay, so y is equal to 125 times 1.05 t, and I can look at that for different time periods. So we're going to find the account balance after 1 year, 2 years, 5 years, and 20 years. Right, so it's pretty simple if I go ahead and plug in 1. So let's go ahead and look at this for 1, 2, 5, and 20. So you can get the sense of what the compound interest thing is all about. When it's t is 1, then I just have 125 times 1.05. And that's 131.25. When time is 2 years, I'll have 1.05 squared times 125, 137.81. When t is 5, I'll have 1.05 to the 5th power. Looks like I made a mistake there. I'm going to redo that. 1.05 to the 5th power times 125. 159.54. And after 20 years, times 125, I'll have $331.66. Now, what's important to know is that I haven't added any more principal to this. So this is not like a regular savings plan. This is a one-time deposit and then earning interest and then earning compound interest. So you can see that in the short term, it doesn't have a huge effect, but in the long term, it starts to become more and more important. Okay, and that's working with exponential growth functions and compound interest.